Welcome back, students. In the last lectures, we have developed a definition of spontaneity based on the Gibbs free energy. Today, we are going to investigate this spontaneity in terms of the equilibrium constant. So the learning goals for today are going to be to apply and derive this equilibrium constant. We'll focus on this Kp, which is an equilibrium constant related to the pressure of the components. We'll also want to be able to distinguish between other types of equilibrium constant that we can calculate, and we'll show this when we get there. We're going to want to be able to explain Le Chatelier's principle, both in terms of products and reactants, but also in terms of things like temperature and pressure and how those affect reactions. The equilibrium constant equations will explain that to us. And then lastly, we're going to be able to defend the exclusion of solids and liquids from equilibrium constants, something that you're probably familiar with, but maybe you didn't exactly know why we did that, just that we did that. What does spontaneity mean for us in chemistry? We know that a spontaneous reaction has a negative delta G, but what does that mean? We have previously discussed that spontaneous does not mean rapid. Spontaneous reactions often need the input of energy to begin, but once begun, they continue to react on their own. Likewise, spontaneous does not mean that the reaction will go completely to products. A spontaneous reaction will have more products than reactants at equilibrium, but not likely 100% products. So for a definition of a negative delta G for us is that given enough time, more products will be formed in a chemical reaction than reactants. And like we just been talking about, a negative delta G does not mean that a reaction will be fast or that it will go to completion. So then how do we know how much products are formed in a reaction? As chemists, this is something that is very important to us. We might be trying to synthesize some molecule or make some product, and we want to know how much we can actually expect to get. And delta G is not enough information to tell us that. If we have a delta G of negative 10 kilojoules per mole, that tells us the reaction is spontaneous, but it doesn't tell us how many products we should expect. And to do that, we need to consider the equilibrium constant. You may remember from general chemistry that the equilibrium constant is related to the Gibbs free energy, and today we're going to derive that equation and see how we can relate the two. So we'll start by considering the textbook arbitrary chemical reaction where we have component A plus component B makes component C plus component D, and we have lowercase a molecules of A in the reaction, lowercase b, and then C and D and so forth. For this purpose, we are assuming that all of our reactants and products are gases. There are plenty of reactions for which this is true. There are plenty for which this is not true. So we're going to start with the gas phase reaction before considering other types of reactions. We're also going to assume right now that the total pressure of the reaction mixture is 1 bar. This does not have to be the case, just makes the math a little bit simpler. And then later on in the class, we'll consider situations outside of 1 bar. The delta G of this reaction is simply the sum of the Gibbs free energies of formation for all of our reactants and products, of course, multiplied by their stoichiometric coefficients. So there's a lot of math here. We're going to go through it one step at a time. We're going to focus here on these first two terms. That is the Gibbs formation energy for component C. So here we have this mu naught C. That's simply the standard chemical potential for C under standard conditions. The important part of the standard conditions here is 1 bar pressure. Then we have this other term over here, RT natural log of PC over P naught. This is a correction term reflecting that our partial pressure of C is not at 1 pressure. It's at some different partial pressure. We have to multiply by C because C is the stoichiometric coefficient, this nu I here. We do the same thing for D and A and B, and we note that A and B have negative stoichiometric coefficients because they are reactants, and that's the definition of our nu I. It's the same as we've used for enthalpy and entropy in the past. Looking at this equation, we can see that there are 8 terms. We have 1, 2, 3, 4, 5, 6, 7, 8. 4 of these terms are simply the standard state chemical potentials of the substances. And with those 4, so with these simple mu terms, if these are the standard state chemical potentials, if we group them all together and had C mu naught C plus D mu naught D minus A mu naught A minus B mu naught B, that is simply the standard state Gibbs free energy. And so we can group all four of these terms into this delta G naught of our reaction. With the remaining terms, we pool them together using log properties. So we take our PC over P naught, raise that to the C exponent here, and then multiply by PD over P naught raised to the D, and divide by A and B since they are subtracted from the terms here. And that boils down this 8-term equation into a 2-term equation. So the delta G of the reaction is equal to the delta G naught of the reaction plus this correction term accounting for the actual partial pressures. And so this is RT natural log of this mess in here. And we can simply take this whole big bracketed term here and represent it as QP, which is the reaction quotient. And the P tells us that it's based on pressures. Now we can note something interesting here. This demonstrates a couple of very important concepts. First, there is a subtle difference between the delta G of reaction and the delta G naught of reaction. The delta G naught of the reaction is the free energy under standard state conditions, namely when each component of the reaction is at a partial pressure of 1 bar. Delta G of the reaction, this one here, is the actual delta G, the actual Gibbs free energy under the experimental conditions. Spontaneity is therefore determined by the delta G of the reaction, not the delta G naught of the reaction. We can demonstrate Le Chatelier's principle using this equation as well. If we have much more reactants than products, this fraction here, our reaction quotient, is a number that is less than 1, which makes the natural log of that negative. In some cases, this will turn this whole term so negative that it overwhelms a positive delta G naught reaction that can make any reaction proceed in the forward direction to some extent. On the other hand, if we have much more products than reactants, our Q will be a large positive number, which will make this natural log a positive number. And that can counteract even a very negative delta G naught R, which will make a reaction stop at some point. So we can see that we're not necessarily always going towards products or never going towards products. It's a complicated relationship based on the actual components in the gas phase here. And we can see some important examples of that looking at this following table. This is from a biochemistry textbook, and these are all the enzymes involved in glycolysis. And what you'll remember from biochemistry is that glycolysis happens, and it's very important. And if it doesn't happen, cells don't get energy. Yet, if we look at the delta G naught for these processes, we'll note that some of them, especially this one here, have very high delta G naughts. And so we would expect that this process would be very unfavorable to occur. But remember, the delta G naught for a reaction is not the actual number that you use to determine whether or not a reaction is spontaneous. You have to consider the actual conditions. And in the cell, the products of this step 4, this aldolase reaction, are very rapidly taken up and continue to be processed. So there's a very small amount of products, which means that the reverse reaction is actually hard to accomplish, and the forward reaction is favorable. So if we look at the delta G's of the reaction under the actual conditions, we'll find that they all are negative or approximately 0. So we get spontaneous reactions despite having a standard chemical potentials that are positive, and in some cases, very, very positive. We'll next consider equilibrium. We define equilibrium as the time where the rate of forming products is equal to the rate of forming reactants, which means that there is no direction of spontaneous change, and delta G of the reaction is equal to 0. So substituting in 0 for delta G of reaction, we can rearrange this expression here to get that the delta G naught of the reaction is equal to negative RT natural log of Kp, and counter to that, natural log of Kp is equal to negative delta G naught reaction over RT. This is the relationship between the equilibrium constant and the standard Gibbs free energy. Note that when we're talking about equilibrium, we take the reaction quotient and put a K there for the equilibrium constant. So K is the same thing as Q, although Q happens at any conditions, any concentrations or partial pressures of all of our reactants and products, and the K is specifically at equilibrium. So they're both equal to this here, but K is using specifically equilibrium values for these things. This equilibrium constant here is the equilibrium constant based on partial pressures. If we have other types of reactions that maybe don't involve the gas phase, or that don't, we want to use a different term, say mole fraction or concentration, we actually end up with a different equilibrium constant. And we're going to go through on the board and see some examples of this. Consider this reaction here. We have 1 molecule of reactant A plus 2 molecules of reactant B react to make product C. And listed below are the partial pressures of all of these components at equilibrium. So if we want to know the equilibrium constant based on the partial pressure, we can simply plug in these partial pressures here and evaluate. So Kp should be equal to the partial pressure of component C over P naught divided by the partial pressure of component A divided by P naught, and then the partial pressure of component B divided by P naught squared, since there are 2 molecules of B involved in this reaction. The P naughts here are always the standard state pressure of 1 bar, and so we often don't include those when calculating the equilibrium constant. They're there to be formal and make the units work. The equilibrium constant is a unitless number, but since they're 1, we often don't put them in the calculation. So we can also write this then as PC over PA times PB squared. We have all these numbers, so we can go ahead and plug them in. We'll have 0.41 divided by 0.75 divided by 0.13 squared. Plugging these numbers in here gets us an equilibrium constant based on partial pressure of 32.3. You'll note that equilibrium constants greater than 1 mean the reaction is spontaneous and will proceed towards the product. Equilibrium constants of less than 1 mean the reaction is not spontaneous and the product would actually go towards the reactants. How would this change if we base this off of mole fractions instead of partial pressure? Well, the mole fraction of component A is simply equal to the partial pressure of component A divided by the total pressure, which is the sum of all of these various partial pressures. We can calculate that to find out that the mole fraction of component A is 0.581. We can do the same thing for a mole fraction of B and say that it's 0.101, and the mole fraction of C is 0.318. So if we wanted to take an equilibrium constant based off of the mole fraction, we could do that. We could say it's Kx, and it would simply be Xc over Xa times Xb squared. And we can calculate an equilibrium constant based off of the mole fraction. Plugging in these numbers, we get 0.318 divided by 0.581 times 0.101 squared. And if we do this, we see that our equilibrium constant is 53.7. So it is not the same as the equilibrium constant of partial pressure. So using different units has given us a different equilibrium constant. However, these 2 equilibrium constants are related, and if we did the same math that we just did with using variables instead of numbers, we would find that we can relate the 2. So the equilibrium constant based on the mole fraction is equal to the equilibrium constant based on the partial pressure times the total pressure divided by the standard pressure P naught raised to the negative delta nu, where delta nu is the difference in stoichiometric coefficients. So for us in our reaction here, delta nu is equal to 1 from C minus the 1 from A minus the 2 from B is -2. So in this particular reaction, we could say that Kx is equal to Kp, which is 32.3, times the total pressure. And the total pressure here is just the sum of all the partial pressures, which is 1.29 bar squared. And if we do that, we get 53.7. So we get the same thing. So these 2 constants are related, but they are slightly different. We can similarly define an equilibrium constant based on concentration rather than partial pressure or mole fraction. And that's related to the partial pressure mole fraction if we're talking about gases. And that's equal to Kp times C naught RT over P naught. So we know that our P naught is the standard 1 bar partial pressure, and then the C naught is a standard 1 molar concentration. So again, we don't often write those, and Kc is simply equal to Kp times RT raised to the negative delta nu there. To actually calculate concentrations of substances at equilibrium, it's helpful to use an ice table. We'll do an example of this in class as a reminder. Hopefully you're familiar with these sorts of things from Gen Chem. You can use any unit for your equilibrium constants, and what we'll mostly do in this class is use Kp for gas phase reactions and Kc for solution phase reactions. We can also look at the equilibrium constant as a function of temperature and pressure. And this is another way in which you can demonstrate Le Chatelier's principle. So if we want to take the, figure out how the equilibrium constant is changing with temperature, we can simply take the derivative of Kp with respect to temperature. And what we'll do is take the derivative of the natural log of Kp. And we'll do that because the natural log of Kp is equal to negative delta G naught reaction over RT. And remember, a couple of classes ago, we took a weird derivative of 1 over T or delta G over T. And so here we see we have our derivative of delta G over T, which makes this much simpler. So this process then is simply equal to a negative 1 over R times the derivative of the delta G naught of the reaction over T with respect to T. And we've already solved for what that is. That was simply, if you recall, you can go back in your notes, it was negative delta H naught of the reaction over T squared. So putting that all together, we can find out that the natural log of the partial pressure changes with respect to temperature to the form of delta H naught of the reaction over RT squared. And so if we integrate this, we'll end up integrating d natural log of Kp, and then integrating delta H naught of the reaction over RT squared dt. And what we get when we do this integral is that the natural log of the equilibrium constant at some new temperature T is equal to the natural log of the equilibrium constant under standard conditions, so under 298, because we're integrating from 298 to some new temperature T. And then we'll have this new term that is minus the delta H naught of the reaction over R. And then the integral of T squared becomes 1 over T, or T to the minus 1. So we'll have 1 over T minus 1 over 298. So here we can demonstrate what happens to the equilibrium constant as a function of temperature. If we increase the temperature, this T will be a larger number than this. And so this number will be negative. So this is a negative number if T is greater than 298. So what happens to our reaction? Well, it depends on the sign of our delta H naught for our reaction. If we have an endothermic reaction, delta H naught for the reaction is positive. So we have negative times negative is positive, and the equilibrium constant increases as a function of temperature. This goes right along with what we learned in Gen Chem, that if we have an endothermic reaction, we can think of heat as a reactant. So adding heat should make the equilibrium shift towards the products. Now, if delta H naught of the reaction is negative for an exothermic reaction, we have negative times negative times negative, 3 negatives in there. And that will give us a negative number overall, and the equilibrium constant will decrease, and we will be more likely to get reactants. So for exothermic reactants, where heat is thought of as a product, we see that we favor the reactant side. We can do the same thing with pressure, although it's a little bit more hard to see here. And that's because our equilibrium constant at based on partial pressures has no pressure dependent term. So if we just increase the pressure, so if we have a gas mixture and we just smush it down, the relative ratios of partial pressure all stay the same, and it doesn't necessarily appear like we would increase or change the equilibrium constant. However, if we look at our definition based off of mole fraction, if we increase the pressure here, the mole fraction equilibrium constant is going to change. Now, how is it going to change? It turns out it favors the side of the reaction with the lesser number of substances. So in this case up here, our delta nu was -2, and that meant that we had more reactants than products. And so as we increase pressure, we're raising the pressure to a -2, so +2. So as the pressure increases, this term here increases quadratically, which means that the equilibrium constant based on the mole fraction increases, and we are more likely to get products. And if we look at our reaction, we have less moles of products in this reaction. If it was the other way around, our delta nu would be a positive number. This term would get smaller as the pressure increased, and we would favor the reactants. Lastly here, I want to look at what happens with solids and liquids. So you may remember from Gen Chem that we leave solids and liquids out of equilibrium expressions. Now, why do we do that? We do this essentially because the chemical potential of solids and liquids is not a function of pressure. So we might want to know how the chemical potential of solids and liquids change. It turns out that our relationship here that we derived earlier, dg dp at constant T, so how the Gibbs free energy changes as a function of pressure at constant temperature, is equal to the volume. Gases' volumes change as a function of pressure. So this is actually changing, and we get pretty different values. Solids and liquid volume really don't change as a function of pressure. Of course, they do slightly, but not very much. And so what that means is that if we wanted to say, how does the equilibrium constant change, right? So our dg dp at constant T is equal to v dp. If we change the pressure, we don't really change the volume. And so the Gibbs free energy for solids and liquids is approximately constant. So if we want to say what's the delta G, we would integrate v dp. But as the pressure changes, the volume doesn't change. So the delta G for solids and liquids is equal to 0, meaning they just kind of have one standard chemical potential or value for delta G. And so we can say then that for a solid, the chemical potential at some pressure P is approximately the chemical potential of that solid under standard conditions. So if we have a reaction including solids, let's come up with one. If we have CaCO3 solid reacting to calcium oxide solid plus carbon dioxide gas, how do we describe this process? Well, we do the same thing that we've always done. The Gibbs free energy of this reaction is equal to the chemical potential of the solid calcium oxide at some pressure P, plus the chemical potential of our gaseous carbon dioxide at some pressure P, minus the chemical potential of our calcium carbonate at some pressure P. Using this relationship up here, the pressure doesn't really affect the solids. So we can say that this term here is simply equal to the standard chemical potential of solid calcium oxide. Whereas this gaseous term for carbon dioxide is equal to the standard potential for gaseous carbon dioxide. But then we have another term that we need RT natural log of the partial pressure of carbon dioxide over the standard pressure. And then for our calcium carbonate, it's the same. So we have our standard calcium carbonate pressure or equilibrium constant because it doesn't change as a function of pressure. What we do is we group these three standard terms and say that the delta G of the reaction is equal to the delta G naught of the reaction plus the remaining leftover term, which is simply RT natural log of the partial pressure of CO2. And so in this case, the QP, the reaction quotient or the equilibrium constant, would be simply equal to the partial pressure of CO2 divided by the standard conditions here. So since the concentrations, the partial pressures of solids and liquids don't change, we can safely leave them out of the equilibrium constant for these processes, because all that matters in the equilibrium constant is the change as a function of reaction. We'll leave it here for equilibrium and Gibbs free energy. We'll conclude by going through these points here. The Gibbs free energy and the Helmholtz free energies are components that we can use to relate systems to their maximum work. If there's no work possible, we derive our spontaneity conditions that either the Gibbs or the Helmholtz free energy must always be negative for spontaneous processes. We derive the Maxwell relations, and we've seen them come up now and again. We just saw it here in the past minute with dG/dP at constant T equaling the volume. These are helpful, and they allow us to relate many disparate partial derivatives that come up in thermodynamics. We figured out that the mixing of gases is always spontaneous, so that's not true for liquids because liquids actually interact with each other. And today we just related the Gibbs free energy to the equilibrium constant and used the equilibrium constant to determine the extent of a reaction, so how far the reaction will actually proceed. We'll continue with our next lecture that will go into real gases. So we'll investigate the differences between real gases and ideal gases and the reasons for that. And I look forward to talking about this with you guys in class.